So welcome again to the webinar. Thank you so much for joining us. If you have any questions throughout the webinar, please post them into the chat and we will answer them during the Q&A session at the end. This is being recorded and we will share the link with you after the presentation. Okay, I am delighted to welcome today Dr. Lorenzo Mercolli. Lorenzo studied physics, maths and astronomy at the University of Bern in Switzerland, where he obtained a PhD in theoretical high energy physics. After working in academia and then for the Swiss Federal Office of Public Health in Radiation Protection, he now works as a medical physicist in the nuclear medicine department of Inselspital in Bern. Lorenzo's research focuses on pushing the boundaries of long axial field of view PET-CT with non-standard radionuclides. Over to you, Lorenzo. Hopefully you can grab the screen share.
Thank you very much for the kind introduction. I'll start with my conclusions. So I would like to convey that you should always be aware of the level of personalization whenever you compute a dose for a patient. You should ideally also understand which method for the dose calculation suits your need. And in the end, you should always balance your uncertainties. And yeah, we will see what I mean by this. What I'm not going to say, I will not show you how to do dosimetry for your specific application. Also, this is not going to be a concise introduction to dosimetry in nuclear medicine. There's plenty of textbooks and materials online that you can find on this. Also, I will not talk about lutetium PSMA, single time point dosimetry, or AI. So you need to find some other talk for that. So, dosimetry. Just a very brief recap. When we talk about dose, we usually mean absorbed dose, which is nothing but the deposited energy in a chunk of matter by some ionizing radiation. And this is measured, of course, energy per kilogram, and we usually talk about grays. So this is the unit for absorbed dose. Now, in nuclear medicine, we're often, or for today, we're interested in knowing the dose that is deposited in a patient's body when the patient undergoes some nuclear medicine treatment. Allow me one comment that is important. The dose is essentially a volume quantity. So for the scales that we're interested in nuclear medicine, you can assume a constant density for the matter. This means that the weight here, the kilograms, they turn to be a volume. So the dose is actually very much dependent on the volume that we're considering. And also the absorbed dose does not contain any biology. So there are different dose quantities that we use when we want to take into account the damage that ionizing radiation does to cells or tissue. Now, when we do dosimetry, we need essentially two basic ingredients: the source and, for lack of a better word, the dose distribution. And then we usually go to what's called the mirrored formalism, which can be summarized in this formula here. So what does this mean? We have a dose inside a certain volume that we are interested in, and we compute this by integrating over time. This capital T often is taken to infinity. And so we need to integrate over the time that the source, so this is the activity contained in a certain source volume S, and then we sum over all possible sources. And then we have this S value here, which is nothing but the dose that is generated in the volume V from the source S. So we have some activity in a certain area in the source, and then the dose that is induced or deposited in the volume V is given by this S value. So here you see these two ingredients. So this part essentially is the source, and the S value is then the dose distribution. So the source, well, it's nothing but the spatial distribution of the radionuclide in a patient's body. And of course, we need to know the time dependence of this distribution, and we usually talk about time activity curves. So this is just the time dependence of the activity distribution. And once we do the integral over time, we talk about time integrated activity. In nuclear medicine, we are in the comfortable position that we usually image our patients, and so the source for a dose calculation comes from the images that we take of the patients. And in general, we need multiple time points in order to determine the time dependence of the activity distribution. Now, the dose distribution, well, we can't really measure it directly, at least in nuclear medicine, and we cannot really do calorimetry, or we can't, or we could, but we don't want to implant dosimeters inside the patient. So we somehow need to model or compute the dose distribution. And what we actually want is a macroscopic quantity. So the dose is macroscopic from microscopic dynamics. And what I mean by this, we have ionizing radiation. So these are particles that interact with the patient body, with the matter of the patient. And so we need to somehow model these particle matter interactions. And Monte Carlo simulations are nowadays the gold standard for this sort of problem, not just in the medical field, also high energy physics or many other fields of science rely on Monte Carlo simulations for matter particle interactions. So just very briefly, how does such a particle transport simulation work? So we start with some initial particle. For us, this will mostly be either a photon or an electron. Then we need to sample a certain path length, and this path length depends on the properties of the surrounding material. And then we have an interaction, and this is sort of a point interaction of the particle with, say, an atom, a nucleus, or an electron. And then once we have such a point interaction, well, we just record the energy that was deposited or transferred from this initial particle to the target material. And then we continue. We just sample again a certain path length. We come to another point interaction. Again, maybe we can produce some secondary particles. We deposit again some energy, and then we just play this game over and over again. And in the end, we just see, well, at every point in space, or in every point in our simulation, well, what was the energy that was deposited by all these point interactions? So Monte Carlo simulations, they provide a statistical average of some macroscopic quantity. So for us, it's the dose. And luckily, we are in the situation that the physics is very well known. So the point interactions of photons, electrons, positrons with atoms and nuclei, this is very well known. This is not the case. Be careful if you're looking at hadronic interaction. There, the physics is less well known and not well described. But for nuclear medicine, we are on the safe side here. And then there's another very important condition for Monte Carlo particle transport, that is the distance between 2 point interactions should be longer than the length scale of the interaction itself. And this we can sort of express in this way, is that the de Broglie wavelength of the particle should be smaller than the interatomic distance. So our targets are atoms or molecules, and the de Broglie wavelength sort of is the length scale of our point interactions. And again, for nuclear medicine, there's no problem here. So if you think of 1 angstrom being sort of the typical length scale for an atom or interatomic distances, so this would correspond to a 10 keV photon or 0.1 keV electron. And as you know, in nuclear medicine, we deal with higher photon and electron energies than this one here. So from this point of view, Monte Carlo simulations are perfectly fine for nuclear medicine purposes. Now, of course, there's no free lunch. We are dealing with statistical quantities, so their uncertainties decreases only with 1 over the square root of the simulated particle tracks. So which means in order to reduce the statistical uncertainty of the dose, I need, by let's say half, I need to simulate 4 times more particle tracks. And this makes these sort of simulations quite expensive in terms of computational time. And of course, people have come up with different techniques in order to sort of circumvent this 1 over square root n problem. Now, there are always some approximations. So in these point interactions that I showed you, there are some models that have some approximations. However, again, nuclear medicine, we are pretty much on the safe side with what concerns the description of the point interactions. And of course, there are systematic uncertainties. So if you don't know exactly the geometry and the material composition, well, this will of course affect the uncertainty in your simulation results. Physics, okay, the models have some approximation, but again, we are usually on the safe side in nuclear medicine. One big issue is, of course, the source, because the Monte Carlo simulation doesn't know anything about the source. You need to provide the source as an input, so you need to say where do I need to start my simulation with a photon or an electron at which energy. So whenever you don't know exactly your source, well, of course, this will have a rather big impact on the simulation result that you get out at the end. Now, just a few comments. I like to think about dosimetry or the problem of computing a dose in nuclear medicine as the source setting the scale of the problem, and the dose calculation or the calculation of the dose distribution should then be adapted to the scale set by the source. When we think about personalization, of course, we can have both the source and the dose distribution taken from some population average or really from the patient we're looking at right now. I would like also to point out that dosimetry is very often a procedure. So we don't have the means to really say, okay, this is the best, most accurate, most precise way to compute the dose. We often don't know. So what we can do, well, we can sort of agree upon a certain procedure. So this is always important to keep in mind that very often we just don't know what is the ground truth, or we don't know what would be the most accurate way to compute the dose. So how can we now personalize a dose estimate? So let's say I want a dose. I have a patient that underwent some treatment in my department, and I just want a dose. I don't want to be too specific on what kind of dose, but let's say I just want a dose. So the first step is to go to this document here, the ICRP publication number 128. So the ICRP, this is the International Commission for Radiological Protection, and they made a document with lots of tables, and these tables contain, so if this information here, this is the example for iodine, and they have all these numbers, and these numbers are a conversion factor that converts the administered activity to gray. So I know usually what activity I gave to the patient, and then I can just go to the table, pick the right radiopharmaceutical, and then, for example, for the brain, multiply this activity with this number here, and I get the dose for the brain. Now, this is nice, very quick. There's no very simple. I just need to multiply two numbers. Yeah, there's hardly anything simpler than that. But of course, yeah, we need to ask, well, how patient specific is this? So I gave some activity to a patient. Well, is the dose that I get out from these tables, how close is this to the true dose that the patient got? So we can check, and then we see that as the source, the ICRP 128 takes the time integrated activities either from the literature, or they do some modeling. So here I put, for example, their biokinetic model for iodine. So they do all these calculations. Sometimes it's also based on measurements. Sometimes it's also some surrogate quantities like blood flow. So this is somehow an average time integrated activity that the ICRP gets mostly from the literature or through their own calculations. Now, what about the dose distribution? The ICRP computes the S values with Monte Carlos, which is nice. However, they compute it for a standard human. So what the ICRP did, they defined, they call it reference computational phantoms, like the one that you see here. So this is just a phantom with some dimensions, organs that have been defined. And for this phantom here, they computed all the S values. And so they can compute all the doses from the time integrated activities that they used. Now, this human phantom here, yeah, it's some average over some kind of population. So if we ask how patient specific is the dose that we compute with the ICRP 128, well, not much. The source is some average quantity, and the dose distribution is also coming from a standard human phantom. So yeah, this is not very patient specific, but it's very quick and very easy to do. Of course, now the question is, well, yeah, can we improve on this dose estimate from the ICRP? And the first step towards having a more personalized dose estimate is the source. And this is actually the concept that most standard software packages that you can buy on the market, they do. So they usually take a personalized source for each patient that you can put in, and then computes the dose from actually standardized S values. Usually you can pick different phantoms, but it's still the S values are standardized for some standard human phantom. Now, so how does this work? First, we need to measure the activity distribution in the patient at multiple time points in order to, know the time dependence of the activity distribution. There are many challenges in here, so you can actually, you need to have a quantified image. So with SPECT, you can do that, but you don't want to have just counts as a unit of your image. You really want to have becquerel. You need the source. You need to take care of the registration. So if you have multiple time images through multiple days, the patient, of course, doesn't always lie the same way on the patient bed. So you need to take care of the registration as well. Next, you need to segment your source. So you have, this is an example from the Hermia handbook actually. So you have these multiple time points and different images. So in every image you need to segment your source organ and also the target organs, but that's less of an issue. Then you need to get the time activity curve from the segmentation that you did. And also here, again, there are many ways how you can do that. Depends at which point in time you took the images. You have to fit somehow very few points with often a nonlinear function. You need to choose a way to do your time integration. So there are many choices that you have to do, because otherwise you can't compute anything. But these choices are not always obvious, or it's not always obvious which choice is the best one. But let's say, okay, you have your time activity curves, you have a certain concept or a model for the time integration, and then you go to big tables where you will find S values for the reference phantoms, for the standard human phantoms of the ICRP. You multiply your time integrated activity with the S value and you get a dose estimate. So this is nice. So we have now a dose estimate that has the source from each patient. However, the S values are still pre-computed from the reference phantoms. So is there a way to have a more personalized S value? And yes, there is a tweak, or there's a little shortcut that you can take. Remember that at the beginning I stressed that the dose is a volume quantity. So what we can actually do is we take the reference phantom and then we simply scale the organs, or the size of the organs of the human phantom, of the reference phantom, to the organ size of our patient. With that, we sort of take care of the difference between, say, the size of the kidney in the human phantom and the patients that we have in front of us. Now, of course, this is mostly a bad fix, because okay, you just scale the volume of the organ. However, the location of the organ, the distance between two organs, this is not taken care of. So yeah, this scaling is simple, it's effective, but yeah, it remains a bad fix. So can we do better than that? And yes, we can do better. We can try to do what's called voxel dosimetry. Now, in voxel dosimetry, we consider each voxel in an image as a source and a target. So for the source, we need to find a time-integrated activity for each voxel in the image that we took of our patient. Now, of course, you can already tell from the start that to fit each voxel and then do a time integral, well, inevitably there are going to be huge uncertainties there, especially in voxels where you have little uptake, so you will essentially end up fitting noise. So this can be an issue. There are ways to take care of this, of course, but it's to keep in mind that whenever you start fitting time activity curves and computing time integrated activity for each voxel, there's quite some modeling and quite some assumptions that go into this. Okay, so now we have our source. Every voxel is now a source, and we can also compute each voxel as a target. So we have our image of the patient, and now each voxel has to be a target or a volume of interest for each voxel source. And this is now nice because it's very patient specific. So we need the image and we compute the dose for every voxel. And of course, we can then try to do again full Monte Carlo. And this is also, there's something for free here, because usually when we do a SPECT CT, well, we have also the CT image of the patient. And the CT image is exactly what we need as a material distribution as an input for the Monte Carlo simulation. However, if we want to do now a full Monte Carlo simulation with each voxel as a source and each voxel as a volume of interest, well, this is going to take quite a while to compute. And that's why people came up with ways to sort of circumvent this computation time. And one crucial observation by these gentlemen here is that, well, what's the source? In nuclear medicine, the source is usually given by a series of SPECT CT images. And, well, again, the source sets the length scale of the problem. So the source is actually driven by the resolution or the voxel size of the SPECT image. And now we can go and check how this looks like for lutetium. And I did a very quick simulation here. So what you see in these images are the particle tracks of a Monte Carlo simulation of lutetium. And this here are the electrons. And so you see these squares here are 1 millimeter. So you see the electrons, they don't go very far. However, the photons, they go much, much further. So the length scale is the same. So yeah, I hope you can see it. The squares are still 1 millimeter in size, but there are hardly any photons interacting within 1 or 2 millimeters around the source. So the electron range, at least for lutetium, is much smaller than the voxel size or the resolution of a SPECT image. And the idea that these people had is to separate the transport in matter of the photons and the electrons. And they call it semi-Monte Carlo. Semi-Monte Carlo because the photons are still transported and simulated like in a full Monte Carlo. So point interactions, sampling of the path lengths, etc. However, the electrons, they're not simulated at all. So we have a voxel, we have some activity in that voxel, so the dose of the electrons is just deposited locally in that voxel without ever simulating the point interactions of the electron. And this is actually very nice because, so in nomenclature of Monte Carlo people, this is a nice example for a variance reduction technique that is very specific to the problem. So you need a source that has a resolution that is not, it is what it is, but the electrons have a smaller range for the way that we compute the source. And the other nice feature is that this has been implemented in HMS, so it's also quite convenient and easy to use. So that's how it looks like in HMS. You can even tweak your photon Monte Carlo parameters. And what you get at the end is a three-dimensional image that is computed within a couple of seconds. And this image now has, as units of each voxel, grays. So this is now a dose map, and you can segment now your organs and get the dose for this organ. Now, of course, first thing you're going to ask, well, how do these methods compare? And there has been a nice comparison in the literature where they compared the Olinda dose, so the dose that is computed with a personalized or patient-specific source from images, but then the S values from the reference humans, with the semi-Monte Carlo, and you see for the kidney dose, so the crosses and dots are left and right kidney, and yeah, it checks out. So these two computational methods, at least for lutetium, I believe it's in this publication, it's for DOTA patients. So we get a fairly consistent picture. Now, does this work also for something else than lutetium? So in CIRT, what we usually do is we deliver microspheres with yttrium-90 directly to the tumor inside the liver. So these microspheres, they just flow with the blood, and then they end up in the small blood vessels in the tumor. So on one side, the source is quite easy because there's no uptake, there's no washout. So once the microspheres are in their location, there's just the physical decay of the yttrium-90. So the time dependence is rather easy in this case. The exact location of the microspheres, we still need to get that from imaging. So we need to somehow make an image of the liver. And there is a challenge here because yttrium-90, if we do a SPECT image, it's just Bremsstrahlung, so the quantification comes with some challenges. For PET as well, I will tell you more in a minute. Now, what we do in CIRT, so the standard way to compute the dose, is to use a constant dose factor. So it's just yttrium-90, a certain amount of activity in a given volume. We can convert that with a constant factor to grays, to a dose. However, we will still need a patient-specific information because we want to usually estimate, well, what's the dose in the different compartments. And by compartments, I mean either the whole liver, tumor, or then there are perfused volumes, there are necrotic volumes. And what is usually done is to take only the relative activity or relative counts, actually. So when you don't have a quantified image, you can still use the information about the location and just take the relative counts for each compartment and then multiply them with this constant dose factor, and you get an individual or a patient-specific dose estimate. Now, with yttrium 90, there's an interesting thing. We can also do a PET image, and the challenge there is that the branching ratio for production of positrons is very small for yttrium 90, somehow 10 to the -6 or so. However, the long axial field of view PET-CTs, they have such a huge sensitivity that we can actually overcome this low branching ratio of the positrons. So begs the question, well, can we do nice voxel dosimetry with yttrium 90 when we do an image with long axial field of view PET-CT? So this is what we did, we tried. However, the first observation is that compared to lutetium, the energy of the electrons that are emitted from yttrium 90 decay is much higher. And you can compare here, so this is again the electron tracks in water from lutetium. So again, we have this 1 millimeter grid here. Here we have also a grid with 1 millimeters, but you see the tracks, the electrons, they travel much further for yttrium 90. So, well, is the semi-Monte Carlo still working? And this is exactly what we wanted to find out. So what we did, we compared the local deposition model. So this would be just the CT image of the phantom, segment the spheres, and then use this constant conversion factor from activity to dose. And we compared this with the semi-Monte Carlo method, so where we took a PET image of the phantom, and we fed this to the semi-Monte Carlo algorithm and computed the dose in the spheres. And then as a reference, because it's a phantom and because we know what the activity was inside the phantom, well, we could do really a full Monte Carlo simulation, which we took sort of as the ground truth in this study. And this is what we found. Well, the blue bar here, that's the full Monte Carlo simulation. And of course, compared to the local deposition model, this is the red bar here, you see that for the smallest sphere, the local deposition model is not able to capture the dose spill out. So it will overestimate the dose compared to the full Monte Carlo. As the sphere diameters increase, well, the spill out becomes less relevant, and relatively to the full Monte Carlo, also the local deposition model decreases. If we look then at the semi-Monte Carlo, so these are these other bars here for different image reconstruction parameters, well, you see that almost for all sphere diameters, there's an underestimation of the dose. So of course the question is, well, what is happening here? Why is the semi-Monte Carlo underestimating this dose? And what we did then, we checked with a perfect PET image. So we generated a PET image which has just perfect spheres with the nominal activity. We fed this to the semi-Monte Carlo algorithm, and this is what we got. So the first two bars are the full Monte Carlo, and you see again the same effect. So for the small sphere, the semi-Monte Carlo is not able to capture the spill out of the dose, because the electron dose is just deposited locally. Well, the spill out is not modeled, so that's why for the smaller spheres, the semi-Monte Carlo will always overestimate the dose. However, as the sphere diameter increases, well, the spill out dose becomes less relevant, and we have almost the same dose from the full Monte Carlo simulation compared to the semi-Monte Carlo. Now, some comments here. You might know that just filling an NEMA image quality phantom with yttrium 90 is still a very challenging imaging situation, even for long axial field of view PET-CTs. And one issue here is that the positrons that we actually then measure in a PET, they come from the pair production from very high energy photons, which means that, okay, the production of the electron-positron pair can be quite distant from the location of the actual yttrium-90 decay. Then for the small spheres, we start having voxelization effects. Of course, if you have a sphere with 1 centimeter diameter, you have a voxel size of 1.6 millimeters. Well, yeah, there is some voxelization effect, which especially for the dose, since it is so much dependent on the volume, well, it will affect quite a bit our dose estimate. This I already told you, semi-Monte Carlo is okay for a perfect image. And of course, if you start looking at larger volumes, which we did in the patient data, so we typically have larger tumor volumes, then okay, this also softens the problem of having spill out or not considering the spill out dose. Good. So what about dosimetry in diagnostics? I'd like to discuss the example of rubidium. So the first question is, well, rubidium, it's a PET tracer for cardiac imaging with 1.2 minutes half-life. So who cares about the patient-specific dose? Because half-life is so small, so the dose is going to be very small. Why should we actually care about looking at patient-specific dose estimates? So one thing, if we go back again, first step, ICRP 128, and we see that the dose estimate there is mostly based on blood flow data, and which means, okay, they know the blood flow in our heart, and this was used as a surrogate quantity for the distribution of the rubidium. Is this good? How accurate is this? I don't know. What's for sure is that the ICRP always tries to have a more conservative estimate of the dose. Now, maybe we don't want to have such a conservative estimate because our patient population that comes for a cardiac PET is not the same patient population as your standard oncological patient that you usually have in PET. And then there's one nice thing that we can do here in Bern is that since nowadays coronary artery disease is considered as a systemic disease, it's good to have an image of all major organs, and this we can actually do with long axial field of view PET. So this is how it looks like. So you see the time evolution of the tracer. The source, well, yes, we have rather good control of the source because the patient doesn't move. So it's one scan. We can separate the one single scan into different time points. And as you can see here, this example for some organs, yeah, we have quite a good control over the dose distribution. And then we can again play the same game. We can compare the ICRP 128 dose with the dose from Olinda, so with the patient-specific source, but standard human phantom S values with sort of the fully personalized voxel dosimetry. And we get again a rather consistent picture, especially if you compare the Olinda doses, which are usually the first two bars here with the second two bars. So it's always rest and stress image. So we get a fairly consistent picture. Compared to the ICRP 128, this is the red dotted line. and dashed line. So you see there are quite some differences to the ICRP dose estimate. So let me wrap up. I tried to convey that you should always be aware of the level of personalization that goes into your dose estimate. Ideally, you should understand or choose the method for computing a dose estimate that suits your need for the level of personalization. And ideally, all the uncertainties that enter your dose estimate should balance each other out. And I showed you a nice example where sort of the uncertainties of the SPECT resolution balances out the semi-Monte Carlo algorithm, the uncertainties that we have there by separating the photon from the electron transport. So thank you very much for your attention, and I give back to our moderator.
Great, thanks Lorenzo, that was really interesting. The Monte Carlo images were excellent. It's great to see some proper physics. So while we wait for some questions from the audience, so please feel free to type into the chat or to the questions box any questions that you might have for Lorenzo. I have a few of my own. So I wondered, the study that you did on CERT dosimetry using the PET for that, completely appreciate everything that you said, and that for sure if you prescribe a known activity to a known volume, you're going to get a better dose than the PET image is going to give you. Clinically, do you think, I mean, do you trust the estimation of that or the measurement of that quantity? So basically you'd have to know what you've given to the patient, which would rely on you correctly assaying the yttrium-90 that you administer before and any residual after that might be in tubing. Do you think that that's, it's still better to do it that way than to rely on the PET's scanner's image?
I don't know. As you point out, the uncertainties in measuring the dose in a vial or syringe in the well counter, for yttrium-90, there are really huge uncertainties there. The PET image quantification, yeah, it's good. However, yeah, you have still the challenge of small branching fraction and the sort of spread out of the distribution. What is better? I don't know. Difficult to say.
That's interesting. So, yeah, one of the reasons that I'm asking is that Hermes are in the process of developing an application, especially for CERT dosimetry, and currently we allow both methods, and we give it to the user to choose which is best, because we don't know either. Yeah, that's great, thank you. Just to add to your point on voxelization, that's a really excellent point to make, thank you, about the small regions. I think a lot of people don't appreciate how difficult it is if you have a very small region that you've drawn in any bit of software. So that software algorithm application has to choose the voxel grid that it's going to create the region on, and sometimes that's smaller than the voxel grid of the underlying SPECT or PET image, so that you can get a smoother outline rather than one that looks blocky. And so the size of that grid is different between different applications, and that can give you different volumes, which then of course affects your dose calculation. And also what happens to boundary voxels. So if you've drawn a nice smooth boundary and yeah, you have a voxel on the boundary, what counts as in the region and what counts as out is different in different applications, which can then also give you a different number. Yeah, so it's a minefield for small regions.
Yes. I mean, for that, lutetium is excellent in that way, because yeah, you actually don't have to deal too much with these sort of problems.
Actually, perhaps I can squeeze in one more question here before I go to the audience questions. So partial volume correction, do you believe in recovery coefficients? Would you like me to explain?
Well,
like the idea that you can, you've done a nice quantum scan and you know what
I mean,
the recovery.
Especially in PET, it's in the clinical routine. Well, the recovery or the PSF correction is done for fluorine 18. So you could, and there's a vast literature on that, improve a lot if you would always use sort of a dedicated point spread function for the isotope that you're imaging. It's not always done.
So you mean to apply it during the reconstruction rather than
yes.
a post? So exactly. Often we get asked, so this is coming from a point of Hermes support for dosimetry applications. People like to draw their small region and on an already reconstructed image and say, I know that this doesn't contain all of the activity. I know that half of it has spilt out, and therefore I multiply the activity in this region by 2, and then that gets the right answer. I don't believe that's a very good thing to do, but people ask for it.
Yes, I mean, you should draw your ROIs according to what you believe the dose distribution is. I mean, the radiation oncologists, they have a whole system of margins to when they segment things, they right. Draw margins. I don't see that being used in nuclear medicine, so there might be an opportunity for a change in culture that we sort of should use maybe more regularly and more consistently margins in our segmentations.
Yeah, that's a good idea. Okay, I'm just looking at the questions that we've got. So we've got a question that thanks for the nice presentation. I wonder if yttrium-90 is a beta emitter, how can we use PET for quantification?
So the thing with yttrium is that with very small probability, the yttrium decays to an excited state of the daughter nuclide. And this excited state, when it de-excites, there's a very high energy photon that is emitted. I think it's about 2 MeV. And this photon can then do pair production because it has an energy that is larger than twice the electron mass. And so we get there a positron, which then will annihilate, and this we can image with PET. But this is a property of the yttrium-90, so it's not a property of all beta emitters.
That's great, thank you. We have another question. Is it possible to use a single PET-CT image for dosimetry? For example, in a clinical study, we have just a single PET-CT image after 1 or 2 hours post-injection. How can we get a tag?
So for yttrium-90, this is what you do, because you know the time dependence. It's just the physical decay of yttrium-90. So for that, for the CERT, exactly, it's that's what you do. You do one PET image to sort of set the scale and for the quantification, and then the time dependence is just the physical decay of yttrium. So for CERT, this works really well. This is what you should do. You can do more, but it won't add much more information. You will very likely just see the physical decay of the yttrium if you do multiple PET images. Okay,
we have a clarification for gallium-68. I guess, do you mean PSMA? Sorry, I was asking the person asking the question.
Okay, yes. So there, it depends how you do your PET scan. For gallium, yeah, there's physiology, there's uptake in organs, there's washout. So certainly you need more than one time point. However, you can, if you do a dynamic scan, well, you have you can reconstruct one scan, but at multiple time points. So you have multiple images from one scan, and that's perfectly fine again.
Do you think you would get far enough out in the, so if it is gallium-68 PSMA, would we need to not be hitting, so for tumor dosimetry, do you think it would be sufficient with the half-life of gallium-68, only 68 minutes, to actually hit the tumor peak? I'm
not sure. You have to ask clinicians. But I think
my thinking is that it would need a bit longer than...
the uptake for PSMA is pretty quick. So
okay. Oh, maybe possible then. Great. I know that, so for the lutetium dotates or dotapeptide treatments, the group, the Hanscheid group in Germany, developed a single time point approximation, but it relied on the image being taken at 4 or 5 days post-injection, yes, so that you had reached kind of the mean residence time, and then other approximations in the method are minimized at that point.
I mean, this is currently a hot topic, how you could somehow have a better estimate of the time dependence of lutetium with just one post-therapy scan.
Absolutely. Okay, great. I think we have made it to the end of the questions, unless my co-chairs can see that I have missed anything. Speak now or forever hold your peace. I think we're good. Right, so thank you again, Lorenzo, for that excellent presentation, and thanks everybody for your attention. We will send you a recording link for this, and good evening.
Thank you. Bye-bye.